Several conditions on the stochastic process will be assumed throughout the paper. So the first one is Markov. The second one is the process has monotonic and continuous transitions, which means their conditional expectation operator would map monotonic function to monotonic function and continuous function to continuous function. And also they should have full support. And two examples of the thing that satisfies all those will be additive and multiplicative random walks, and the proof is given in a paper by Cruz and Strack. In some of the examples, I will assume the stochastic process martingale as well. So I will first restate some of the results from a paper by Cruz and Strack, which has a similar model. So the main difference is in their model, the agent could only choose to stop or continue at each time. So it's equivalent to having only one possible terminal action. So after she stops, she can only choose one thing. And the main result from that paper is if the expression here, which they call it the marginal incentive function, which is basically the expectation of the utility next time minus the utility this time. So the main result is if this thing is non-increasing, then a stopping rule is implementable if and only if it's a single cutoff rule. And something nice they found is also include a closed form expression for the prices or the transfers. So in my paper, I slightly extend their model to include multiple possible terminal actions. So for simplicity and for the purpose of this presentation, I will assume that the Q is a continuous interval, and the Q function should be continuous and differentiable. So one assumption I make is this cross derivative condition on the utility function. And the two main conditions that I will have for the single cutoff rule is first the Spence-Merlis condition, which basically says Qt is increasing, and the second one is a single crossing condition. So I label this Pavan, Siegel, and Toika because in the paper by Pavan, Siegel, and Toika, they have a single crossing condition that looks similar as well. So since their model is slightly different, so the condition is not exactly the same, and I think it's not even this is not even a simplified version of their single crossing condition, but the form of the expression looks similar. So I will call my single crossing condition the PST condition. And one function that needs to be defined is the impulse response function, which is only a function of the stochastic process. So one way to think about the explanation of the single crossing condition is this expression here is kind of monotonic in T. So this is monotonic in X, and this is monotonic in T. So the main result I'm going to state is under the previous assumptions, the Qt satisfy the Spence and the PST condition if and only if this pair of stopping rule and terminal action is implementable for all single cutoff rules tau. So I will give one example here. So suppose our utility function is given by this. So here it means it's discounted Q is the investment multiplied by the value of investments, so subtracted by some cost of collecting information, say. And also suppose our stochastic process is some kind of additive random walk, then the first condition, the Spence condition, is the same. The second condition, the single crossing condition, can be simplified and has an explanation. So here it means the current investment should be larger than the discounted expected investment in the next period. So what the main theorem says is if these two conditions are satisfied, then all the single cutoff rules are implementable. And also, if all the single cutoff rules are implementable, then these two conditions must satisfy. So note that the converse is not that strong because it's not a necessary condition for implementability of each one of the single cutoff rules. But if all of them are implementable, then these two must be satisfied. And also, a modified version of the closed form formula for the prices in the Cruz and Strack paper still applies.